Okay, so welcome to my talk. I want to discuss a bit a line of research that is concerned with trying to get quite precise understandings of larger classes of polynomial time problems. And we draw, as Dor already did quite nicely, some parallels to classical results on constraint satisfaction problems. So maybe to motivate this line of research a bit more clearly, I want to first philosophize a bit about the state of the art of the hardness in P field. So here we have a couple of tight conditional lower bounds in the quadratic time regime, for example, for threesome, which we've discussed today already, or the orthogonal vectors problem, APSP, so a bunch of tight relationships between quite a diverse set of problems. So this is quite nice, but you might want to make a point of critique that in some sense we take some isolated problems and we try to establish some relationship between them, and it seems like you really take just very separate problems and you try to see what you can say about them. So this is maybe a bit different to like a classical NP hardness proof, where once you reduce 3-star to a problem, you in fact reduce the whole class of NP to this problem. So you could say we only derive these isolated kind of reductions between problems. There are, of course, exceptions to this rule. So for example, it's more than just isolated reductions. For example, if you look at the subcubic equivalences of a certain matrix problems, then it's essentially independent of what semi-ring you're working over, or the work on sequence similarity measures. You can try to come up with a kind of abstract technical conditions which problem needs to satisfy, and once they do, then you immediately get a very strong kind of hardness for this problem. Or in recent results, a recent line of research kickstarted by Aviat and Ramir particularly, you could, for example, have the philosophy that once you fix a notion of a communication protocol, you can come up with an arbitrary communication protocol in this setting, and this gives you reduction, for example. So there are some exceptions to this rule, but mostly these classes are kind of like not syntactically defined. You really need to manually prove that some problem is amenable to a reduction in a certain sense. So I'm asking kind of, can we get a bigger picture of complexity in the polynomial time regime? And so recently there's been a major step performed in this direction, and it is very connected to the relational database questions from before. So let us talk about first order properties. So I'm talking here about just some, we have some variables that are either existentially or universally quantified over some set of objects, and then I have an arbitrary Boolean predicate expression involving some predicates, or I will call them now relations, over these objects. And so once we fix such a property, then this immediately gives me a model checking problem. So before we were more concerned with enumeration problems. Now we just want to answer whether this property holds. So here we are given our input instance, our database, so in the sense how these relations are defined by simply giving the list of all tuples of these relations. So for which objects are related. And then we want to determine is this property satisfied. So one example would be the orthogonal vectors problem. Here in a single set variant, we're given n vectors with 0, 1 entries in d dimensions. We want to determine, is there an orthogonal pair? So here, if we define a relation between objects for the vectors ai and coordinates k to hold if and only if the kth entry of ai is equal to 0, then this property here really precisely corresponds to orthogonal vectors. Are there two vectors ai and aj such that for all coordinates at least one of those two vectors has a 0 entry there? So there's obvious applications in database theory, but you can come up with also properties of sparse graphs, like the k-dominating set problem. You can easily express like this. A variant of the Hetting set problem. So there are really a bunch of problems that you can phrase like this. This gives us a class of first-order properties. And now there's a very simple kind of baseline algorithm for this class of problems, which only depends on the number of quantifiers that I have. So if I start with these k+1 quantifiers, then I immediately get an algorithm that solves such a first-order property in time m to the k. So in particular, so this holds for an arbitrary formula, in particular for this OV property, since it's defined on 3 quantifiers, I can solve it in quadratic time. And now, interestingly, there's the following completeness theorem, that OV belongs to the hardest class, to the hardest problems in this class. Namely, if OV was solvable faster than quadratic time, then in fact we could solve all the k+1 quantifier first-order properties polynomially faster than their baseline algorithm. So now this gives a stronger kind of reduction. Now, whenever we reduce OV to some problem, we in fact reduce all of the first-order properties to this problem. Well, that's quite nice. So now that we have this interesting class of problems, I want to now draw for which OV is complete. I now want to draw the analogy to constraint satisfaction problems, namely, as Dor discussed already, once we fix some relation for a constraint satisfaction problem, we might end up with a hard problem like K-sat or with Horn-sat, and Schaefer's theorem from already the late 70s tells us that there's nothing in between, that either we can give an NP completeness proof or we can really solve it exactly in polynomial time. This has led to the dichotomy conjecture that the same holds for any domain, not only the Boolean one, and has been resolved positively only very recently. So we want to ask the same kind of question also for this class of first-order properties. So can we maybe also really precisely describe this line? What are the complete problems and what are those problems that we can, and that maybe the rest is really solvable faster than m to the k running time. In particular, I would like to find out what is what kind of property makes a given formula hard to decide. So now we indeed get some kind of dichotomy, but so it is a complexity dichotomy first for restricted class of formulas. So what is our restriction? First, we restrict ourselves to look at graph properties. So we only allow a single binary predicate that we might look at as a edge relation. So properties defined on graphs, really. And then we look at properties of the following form. So we have k existentially quantified variables, x1 through xk, followed by a single universally quantified variable y. So why particularly this kind of quantifier structure? Well, this is the quanti structure, the only quantifier structure for which so all known complete formulas for the class of first-order properties has this quantifier structure. And in fact, under a non-deterministic variant of strong ETH, we even can say that this is the only quantifier structure that has complete properties. So this is why we look at this structure before as a first step in this direction. And what we're able to do is to come up with a hardness parameter, which enables us to give the following two cases. Namely, if this hardness parameter is bounded by 2, so it's 0, 1, or 2, then we give a polynomial improvement over the baseline algorithm. And if it's larger than 2, so at least 3, then we in fact give a matching lower bound, an m to the k time lower bound, under plausible assumption, the 3 uniform HyperClique conjecture that we discussed before, in a bit more in a different formulation. So this is not the same question that I started out with, so we could not prove that all of these properties are really complete for this class, so this is maybe this would be quite interesting to see whether this is the case. I personally would doubt this, but this definitely gives us some structure, quite interesting structure in the first order property regime. So maybe let me tell you a bit more words about the three uniform HyperClique conjecture, since it's quite central for the result. So it's, apart from the paper that we, from the previous paper, now these two papers are maybe very relevant. In particular, this very nicely describes the status of this problem. So we are given three uniform hypergraphs, so meaning that every edge connects precisely three vertices. And we can also assume that we are given this in a k-partite form. And here the quest is really to find for every part one vertex, so that all the three variable subsets of my clique of the chosen set forms an edge of G. So trivially, by just brute forcing over all possible cliques, all possible k subsets, we can solve it in time n to the k. And the conjecture is that really for no k, polynomial improvement over this running time is possible. So why is this conjecture believable? Especially given the fact that for k equals 2, for just regular, for two uniform hypergraphs, so graphs, we can find something faster. Well, the techniques for k-clique that give a faster than n to the k algorithm, they fail for hypergraphs. Yeah, these algorithms really crucially rely on fast matrix multiplication, and it's like the obvious road to adapt them cannot work. And also, if we want to refute this conjecture, then we would also need to show that max 3-cert can be solved exactly faster than 2 to the n running time, which is currently not known. Yeah, but still it's easier to refute than, for example, the orthogonal vectors hypothesis, since if we get a subquadratic algorithm, then we could also refute this HyperClique conjecture. Okay, so now let me define the hardness parameter, which is central for this classification. So we're given some property of this form. So let me just give an arbitrarily made up example. So we will define this hardness parameter in 2 steps. So the first thing is that we will replace all occurrences of the edge relation between only existentially quantified variables by false. So with this, we obtain a simpler formula. So here only the implication survives. This here drops out. So we arrive at a simpler formula. And this we can view as a function that just maps k bits to a true or false value. Namely, these bits correspond to whether the edge between xi and y is present or not. So we get some Boolean formula of this form. And now we can define the hardness parameter. It is the maximum value h intuitively such that we can find an h clause on any h variable subset of the variables, right? As a restriction. So in particular, what I mean is if for any subset of all but h variables, I can find values for all the remaining variables such that the resulting restriction has precisely a single falsifying assignment. So, and this definition very nicely connects to a hardness proof. Namely, so now how can I prove hardness of this formula? So I have such a formula with hardness at least 3. So what I do is I take my 3 uniform hypergraph instance, and the idea is that now my x1 through xk choose a HyperClique. And the remaining part of the formula is now responsible to verify that indeed this is a HyperClique. And so for every non-edge, so for every edge that is not present in the hypergraph G, I introduce a dimension that is responsible to check that I did not choose precisely these three variables. If I can do this, then I'm done. And now by our hardness definition, now we can encode a 3 clause precisely on the three variables that encode whether or not I have chosen these three variables. So I will define the values such that really the only falsifying assignment is such that all of VA, VB, VC are chosen. So this is what is now allowed by my hardness. This is quite immediate from the hardness definition. So yeah, naively this gives a non-matching lower bound because I introduce a large number of dimensions, but this is a technical issue that can be taken care of. So the more surprising direction is actually the other direction, that if I have a small hardness parameter, then indeed I can get a polynomial improvement. And I can only sketch the main idea here. So essentially, the main idea is that it suffices to brute force all but three specifically chosen variables. And then I'm left with a three variable property. And I want to solve all of these kinds of properties in subcubic time. And for this, we define a constrained triangle framework. This is, in essence, a quite convenient way to define a powerful problem that we can still solve in strongly subcubic time. And so just to give you some intuition, so the base problem in this framework is triangle finding. So given some graph, here a tripartite graph, we just want to determine whether there's a triangle ijk. So this we can solve in subcubic time using fast matrix multiplication. And then I can define more complex problems by taking a constrained triangle problem. So for example, the base problem of triangle finding. Then I introduce a new weight function. And then I arrive, for example, this is, for example, a nice problem when where I take the original constrained triangle problem, and I additionally require that the triangle that I find not only satisfies this original problem, but also that two of the edge weights are the same. And another problem would be a summation problem where I want to find a triangle that solves the original constrained triangle problem, but also where the edge weights sum up to 0. So this is a zero-weight triangle, which in general is subcubic hard, but here we have an additional restriction that the weights in total should be of bounded size. And so the nice thing about this framework is that now I can define, just by stacking different of these constraints to each other, if I just stack a constant number of these constraints, then still I have a strongly subcubic time algorithm. And so this kind of these kinds of problems are expressive enough to allow us to conveniently solve all of these types of problems. Yeah, for the details, please approach me. So in general, it's now sufficient. This framework is now sufficient to solve all problems of bounded hardness. So in conclusion, what we've seen is this class of first order properties where we really can get this kind of dichotomy result precisely described by a nice hardness parameter. Now, for the future, of course, the ultimate goal would be to really get a precise understanding of each first-order formula by determining the optimal running time here. So give a corresponding time algorithm and a matching conditional lower bound. So currently, we're still quite some way from this. And in particular, the next steps would be to extend our classification when m to the k is really the right running time, beyond graph properties and also beyond this exists k for all quantified structure. And at any point, getting more understanding of the 3 uniform HyperClique conjecture would be very nice. Thank you very much.